All right, welcome everybody and thank you for attending. This presentation will have two parts, one public and one private, each for about an hour. At the end of the public presentation, there will be an opportunity for questions for anybody who is in attendance. So without any further ado, let's begin. My thesis was on the effect of self-reflection on relative student success in Calculus 1. It was completed with the assistance of Dr. Mary Schaefer, who is an associate professor of math education at Northern Illinois, Dr. Dan Grubb, who is a math professor and the calculus coordinator, as well as Dr. Xian Deng, who is the dean of the NIU Department of Mathematical Sciences. For the purposes of ensuring smooth delivery with Zoom, again, I will be muting everybody who is participating. However, if a question arises, you can click the raise your hand button underneath the more menu or possibly at the bottom of your display, and I will check periodically at the end of every section in the slide deck for questions. Now, this study sought to assess the effect of self-reflection exercises on student success in Calculus 1. But more specifically, it sought to assess a plug-and-play classroom framework which incorporated a holistic rubric and corresponding self-reflection worksheets aimed at developing students' awareness to their own conceptual understanding of the material and presentation of their knowledge, all while removing the pressure of performance grades. The results were quite impressive. Those participating in the framework outperformed those who declined the option, as well as two control classes that were not given the option of participating. They had significantly higher pass rates and reported an improved understanding of their abilities and the content. This presentation begins with an introduction to the theory and the research on which the study was based. I then discuss the design of the study and the research questions that directed my numerical analysis. I will conclude with the results of our study and attempt to interpret our findings using contextual backing for my interpretations. Let's begin with an introduction. Robert White, president of the National Academy of Engineering in 1968, stated that it was time to turn calculus from a filter to a pump. However, a study conducted in 2010 and published in 2015 by the Mathematical Association of America says that we seem to have made little progress towards this vision. This survey involved 300,000 Calculus 1 students from colleges and universities across the country. What they found in the classroom is all too familiar. A vast disconnect between students and teachers, a large variety of student abilities and experiences, and teachers struggling to handle both. This resulted in student demoralization, regardless of whether or not the student passed or failed the course. Now the question is this demoralization because math is inherently demoralizing? It doesn't appear so, since Pew Research suggests that out of the 58% of US adults who enjoyed math classes in grades K through 12, most point to the subject matter as being the main reason why they liked the math class, rather than the way that the math classes were taught. So what is the harm? Well, it's not simply limited to the students. Failure to meet the insatiable public demand for STEM talent ultimately affects future job growth. The US's math education has been identified as shockingly below that of many of the world's leading industrialized nations. And according to the career profile in 2019, high-level mathematics courses are required for degrees that correspond with 46 of the 50 top salaried jobs in America. This means that a failure to pass calculus can be directly tied to limited national growth and a lost opportunity for students who wish to affect their socioeconomical status. Let's begin with a student-teacher disconnect. There is a void between the demand and the supply for higher levels of math education, both from a professional and an academic standpoint. Students are flooding the school systems with computer science and engineering programs doubling their enrollment in recent years, and biosciences have nearly tripled. What's more is that this demand doesn't seem to be slowing. In addition, budget cuts have prevented post-secondary education from meeting this demand with lesser student-teacher ratios. When students do enter the classroom, they're often met with poor teaching practices. The MAA stated, for example, that only 34% of Calc 1 faculty report that they often or very often required students to explain their thinking on assignments. So where does this lack of conceptual development take us? Well, for starters, it creates a false expectation that math is something that you do rather than something that you discover. What mathematicians will universally understand is that mathematical discovery is better described as a zigzag versus a straight and narrow path. Yet students are shown lecture-based instruction in which teachers copy well-organized solutions in real time. As a result, students grow to view mathematics as a collection of computations rather than a language that is used to model logic. So what do students who think that they are ultimately responsible for performing do? They naturally develop performance goals, whether this is passing the course or achieving a desired letter grade. You can hear it in their language whenever they say, I just need to get through this test, or C's get degrees. They lose sight of the fact that centuries of instructors have chosen to present this material because it results in greater awareness of patterns and improved professional practice. When it comes to teachers trying to manage student variety, there are a lot of inputs to consider, each of which produces students of vastly different abilities. Patterson and Ewing reported in 2013 that when matched by ability, students who participated in AP Calculus significantly outperformed their college classmates. However, on the other end of the spectrum, college pre-calculus produces students of a surprisingly lower caliber. In some studies, students who took pre-calculus had a significantly lower success rate in calculus as compared to those who had skipped their recommended remediation. Add to the mix high school pre-calculus students who are learning to balance not only harder material in calculus class, but also a less engaging college classroom. Lastly, consider students who are retaking college calculus and are balancing their demoralization and their desire to disengage from earlier material because they believe it to be easy. Altogether, you have quite a wide variety of experiences and abilities to consider. Further consider that in the classroom, you have students dealing with the burden of college transition. You have students with a variety of different study skills and students who have very different mathematical philosophies. Each of these affects student engagement in the classroom or lack thereof. And engagement is key because without it, students are significantly more likely to drop out of college before their sophomore year. It's no wonder that students are getting demoralized. Sadly, our attempts to reform calculus have had mixed results. Whereas many reform efforts report greater student performance or understanding, they often can't say the same for students' feelings of contentment. Calculus reform courses, for example, report greater student disconnect for an adjustment period of about 2 years. Student contentment rises after this timeline, but that assumes that students remain enrolled in mathematics courses for that long afterwards. Technology, which includes graphing calculators and digital devices, averages no impact on students' attitudes, unless you consider when it's graduate students who are utilizing this, in which case the national average has actually resulted in a negative impact on attitudes. Group work, word problems, flipped reading, and student explanations of thinking have all been shown to average a small negative impact on student attitudes, their confidence, their enjoyment, and their desire to take more math. So, where might hope remain? Thankfully, we do have insight into key factors that may be critical for improving our classroom success, but the research is widely based in K through 12 education. John Hattie is a researcher who compiled 1,400 meta-analyses at over 80,000 studies involving 300 million K through 12 students. And he has compiled over 250 influences and organized them by their effect size. Although all positive effects are valuable, Hattie does draw a line of demarcation at an effect size of 0.40 or greater, stating that whereas any effort by a teacher is likely to result in students performing better simply because of teachers' attention, those factors with a greater effect size than 0.40 signal significant improvement. Above the line are factors such as students' self-reported grades, which has an effect size of 1.33. Student efficacy, or their belief that they can affect their own learning, has a high effect size at 0.92. Also above this line is prior ability and teacher clarity. What are some examples of things that have maybe a less significant effect? Well, homework, which flies in the face of traditional belief that additional worksheets and practice problems are all that's required for success. There are even factors that have a reported negative effect, such as performance goals. Whereas learning goals actually have an effect size of high significance. Hattie's work inspired me in me a need to develop classrooms that captured these positive effects and limited students' focus on performance. So I set out with the goal of developing a plug-and-play classroom framework in which I could duplicate Hattie's performance findings and improve student satisfaction. Now, I called this my self-reflection framework. In short, students were given the option to participate at the beginning of the semester and for a week following each test. They would be responsible for completing assignments and then reflecting on them. In exchange, they would receive credit based only on their completion and their reflection. Performance grades would not be counted until the test. As an additional incentive, students participating were allowed to have retakes on their first and their third test, but only if they showed evidence of having completed their reflection. Retakes on the midterm and the final exam were not permitted, mostly because they were graded by a panel of instructors, and thus retakes would not have been feasible. So let's discuss this study design in a little bit more detail. First, a little context on me as a teacher researcher. I have an undergraduate degree in industrial engineering, and I'm pursuing a master's in math with a focus in math education. At the time of conducting this experiment, I had only taught for one semester previously, and it had been in a Calc 3 classroom. I was teaching Calc 1 while conducting this experiment at the same time as teaching an introductory manufacturing course at the College of Lake County. I have approximately 5 years of experience in a variety of industries, and I often bring this experience into my classroom as an example of math in the workplace. Now, I share this for two reasons. First, it will provide a little bit of insight into my classroom culture. In manufacturing, for example, we did not accept a failure to develop great product, and I do carry this value into my teaching. I believe in pursuing a 100% success rate for my students against high standards, and I work to develop simple classroom procedures. You'll see that this inspiration comes out through the study's design. The cornerstone of this study was its rubric. This rubric was given to all of my students in the experimental class as part of their syllabus at the beginning of the semester. This rubric was unique to my section, and no other sections received this rubric. The rubric itself was modified from one that was developed by Grayslake North High School. It is used so prevalently there, in fact, that this rubric is provided in every guided note packet, and posters referencing the rubric are hung on the walls of each math classroom. It's structured in such a way that students can score themselves easily in the left column depending on the point value of the question. A heading on the top stresses a level of mastery and a brief description of what the mastery means. Here, for example, Mastery Plus is identified by complete understanding and use of the mathematical operations. There are multiple examples of how this could be demonstrated, from correct calculation to clear and organized work. These categories include developing mastery, understanding, incomplete understanding, and no evidence of understanding. But the common theme throughout the rubric is clear communication of understanding. To stress the student's ownership of reflection, a decision was made to provide highlighting feedback only and instead of written feedback. Highlighting feedback drew students' attention to where the mistakes occurred, but not what the mistake was or how it should have been resolved. The goal was to prevent students from simply matching my feedback passively against the rubric. So you can see in the first example, a student attempted to communicate that a limit could be computed by directly substituting for x. However, they forgot to remove the limit notation following this substitution and thus communicated a gap in their understanding. In the second example, the student simply misreads the table and states that a limit gets closer and closer to an incorrect value, which is an overall minor error. However, the concept of getting closer as attached to limits is left unhighlighted to signal that this thinking was correct. Now, all students received the rubric and the highlighted feedback. However, only students who opted into the self-reflection framework were then responsible for completing a self-reflection worksheet. There was often ambiguity that resulted from the highlighted feedback. For example, students had to determine why they were wrong. Was their error a conceptual error or a mechanical one? Did it severely affect the structure of the problems? Many times this forced students to seek help from the instructor or from a tutor, both of which were available. Sometimes the students simply chose not to follow up. Here you can see that a student decided to score themselves at near mastery for question 1, and they still awarded themselves full credit for a 1-point problem. Now, this is a reasonable call and one that most professors would have made, and which corresponded with their rubric. Students could then continue evaluating themselves on a question-by-question basis and in total their score at the bottom of the worksheet so as to better keep track of their performance through the semester. Students would receive half of their credit in their grade for turning in the assignment, and then they would receive half the credit for completing this worksheet. But at no time was there given regards to the score that they gave themselves on the bottom of this self-reflection worksheet. On tests and midterms, students were still responsible for conducting self-reflection worksheets. However, once completed, and regardless of the student's self-grading, the teacher would deliver their final performance grade. This framework sparked many questions. The first was whether or not this option would be attractive to students. The second was, if it is attractive, then to whom? Would there be an effect on performance similar to what Hattie had discovered? Would this affect a student's interest in mathematics? Would students feel that the self-reflection option was to be credited for their improved awareness and their understanding? Would students get better at reflecting throughout the semester? And lastly, what would be the effect on students ultimately passing the course? All right, so let's begin discussing the results of this. Question 1, would students choose to participate in the framework? 15 students opted into the self-reflection option at the beginning of the course, showing that there was a clear majority and allowing me to conclude that this was an initially attractive option. Of the 15 who opted in, 1 switched out, crediting confusion about how the grading structure worked, and another was forced out due to failure to complete the self-reflection exercises. Of the 9 students who originally opted out of the self-reflection option, 1 student chose to switch in after the first test. Students were categorized as shown here by whether or not they spent the majority of the semester in one category or another, although it should be noted that there was very little fluctuation between the categories. Question 2, which students would choose to participate? Might they be more or less mathematically adept? To determine this, original scores were collected for all tests and exams and segregated by their reflection options that they had chosen. Black was those who had chosen the self-reflection option for a period preceding the test, and the red was those who did not. Now, this can be a bit of an eye chart, but what I'd like to draw your attention to is the difference in distributions that both samples have during the first 2 tests and their similarity in the last 2. The self-reflection or the Black distribution has what's called a unimodal distribution, or a bell-like curve, whereas the red group has a bimodal, or a bathtub curve, for the first two tests. When a deep dive was conducted as to why this was, it turns out that the lower mode of the no reflection group, so those scoring averaging less, dropped the course after the midterm, which was when the final university deadline was. The result was that the mostly high performers in the NR group remained, and they closely matched all of the students that were participating in the self-reflection option. You can see this trend continues until the final exam. Now, one possible interpretation for these findings is that students who opted out of the self-reflection option do so for two reasons. Either they believe that they are mathematically adept and therefore don't need the additional, or to exert the additional effort, and this would be the ones who are in the upper mode, or the upper part of the bathtub curve. Or students simply were unwilling to exert the additional effort regardless of the option given, and I'm going to credit this to the lower of the two modes. Those unwilling and less adept at mathematics began to perform significantly worse by the time of the midterm, and they eventually dropped the course. Now, what you can see is that there was no noticeable difference between the resulting high performers from the no reflection group and the self-reflection group at test 3 and the final exam, showing that whereas the no reflection average had dropped to a greater degree, or showing that the NR average had dropped to a greater degree than the SR average had. So in summary, those not participating in the self-reflection option began to perform worse, whereas those in the self-reflection option began to perform better. And we'll see that in more detail on the next slide. Now, a split plot, two-way repeated measures ANOVA test was ran to compare students' relative test scores to distinguish the effect of the class on the student, and then within the class, the self-reflection option itself. Midterm and final exam scores only were used for this analysis so that it would clear up any bias that came from either me as an instructor, as well as given instructors the option of grading on a rubric that was different than mine. Now this, as I said, determined if a panel of instructors without reference to my rubric would report significantly different achievement for the students. Now, what you can see is there's a clear difference in the grade trend between the experimental classroom, in other words, those who were given the option of self-reflection, and the two control courses that we compared against, those who were not given the option to participate. And what you will see is that all the slopes are negative, which is to be expected. The final exam was a cumulative test, and it was approximately twice the length of the midterm, meaning that it was an objectively harder test, and you would expect naturally lower scores. However, the experimental classroom showed a very little drop in their test scores as compared to the first and second control groups. In other words, their grades stayed relatively similar despite the harder test. Now, when the self-reflection group was compared to all students who did not participate in the framework, including those who were not given the option, another significant difference in trend line is observed. Each of these significances were statistically verified, with a p-value that was less than 0.05. What is worth noting is that those with the greatest drop in their scores were those who were not reflecting, who had given up, or those in the NR group who had given up the option of self-reflection, represented by the very bottom row in the table. Now, my conclusion from all this analysis is that students who participate in the option may require a bit of an adjustment period in which they develop their self-efficacy, their awareness. But the result is greater performance over time versus those who are either not given the option or those who decline the option. This is likely because students who believe that they are mathematically adept hit a point of struggle in Calculus 1 after the midterm, which is when the concepts begin to be more critical to success than the simple mathematical mechanics. So performance improvement was significant. What about the framework's effect on math interest? Well, this analysis was severely impacted by the size of our sample. These surveys were given before each test and exam, and students were asked to rank themselves 1 to 5 in terms of agreement with various prompts, but there were only 24 students in the course. This forced students' responses to be similar pretty much by design, and thus it made statistical conclusion difficult. Now, that being said, there were a number of noteworthy comparisons that could still be made, some of which remained statistically significant. Those participating in the self-reflection option averaged a higher level of reported interest in mathematics as compared to the no reflection group, although this was, at this time, was not a statistically significant difference. However, the SR group did report close to statistically significant difference versus the MAA averages with a p-value of 0.06. Therefore, despite the negative effects of a small sample size to our analysis, I can conclude that those who participated had the highest average response to this prompt by the end of the semester, to a point that approached significance against the national averages. Students were again asked to rank their agreement on a scale of 1 to 5, with the prompt being, the self-reflection option has helped me better understand my abilities. Now, there was a risk that students might simply reply positively to the survey out of a sense of goodwill, and this risk came because there's been reports in previous research studies to this effect. So to mitigate this risk, all statistical analyses were conducted to determine if students not only held agreement, but they held strong agreement with this prompt. So the average expectation was set as a 4 out of 5. That is, the null hypothesis assumed that students might answer with agree out of goodwill, but that they would only answer strongly agree if they had favorable opinions. The average agreement was significant at all times when we surveyed. What's more is that the distribution shows a general trend towards the positive over time. Students' latest responses were compiled into a latest category, which allowed us to conclude, regardless of what time they dropped the course or if they completed the course, that students left at all periods with a very positive impression. And as you can see, there were none who replied disagree or strongly disagree with the prompt. An almost identical story can be concluded with regards to understanding material. The average was significantly higher than the sample agreement, with a strong trend towards the positive over time. In fact, not one student reported any level of disagreement with this prompt in either question. Question 7 was whether or not students improved in their abilities to reflect over time. In short, they did not, but they did become more consistent. In each of these graphs, you can see that there is a red dotted line that represents the trend line for a plot of students' self-reflection scores versus teachers' given scores, so a scatter plot. We would expect to see that this red dotted line oriented at a 45-degree angle, which is represented by the black dotted line. This would represent that there had been perfect student-teacher alignment in grading. You can see the curves on either side represent the 95% confidence interval, which the black dotted line clearly does not fall between. The slopes of 0.44 and 0.43 respectively show that students tend to score themselves more favorably versus the teacher, even when it has no effect on their final grade. Therefore, we could not conclude that there had been any improvement in alignment between a teacher and a student's scores over time. Now, that being said, if you direct your attention to the R-squared values in the bottom right, you will see that there is a dramatic shift. In fact, it was statistically a significant shift. This represents that the variation that students and teachers gave to test scores decreased dramatically between test 1 and test 3. So my conclusions are that although students remain unable to effectively determine what they do not know, likely because they haven't taken the class yet, they do become more attentive to the rubric over time, and more aware of their presentation. This decreases their variation. However, it points out a large difference between self-grading, in which case would not have been effective here, and self-reflection, which is what we conducted and is simply an exercise that was. Our eighth question may have been the most important. What is the effect on student success? Here you can see a comparison of the number of students who successfully passed the course with a C or better versus those who withdrew, failed, or dropped the course. There is a statistically significant difference in proportions in favor of the self-reflection option. My conclusion from this is a little complicated. The metric of success is the only one that would have been directly affected by the completion and reflection credit, which gave students a much greater chance of full credit on homework and quizzes. Remember, they were given half their points simply for completing the homework, half their points for reflecting on that, and that did affect their final grade and thus might have had an effect on their course completion. So this would have naturally resulted in the students having more points to count towards their final grade. However, if we recall the earlier performance data, there appears to be no evidence that students were using this as a means of skirting the system. After all, homework and quizzes made up only about a quarter of their final grades, and the largest percentage was determined by the final exam, which made up for about a third. Therefore, I do conclude that this self-reflection option simply gave students the opportunity to develop their self-efficacy and their skill set until they got to a point of naturally higher performance and attention. We did find a number of significant differences between the culture of the classroom and what might have been expected. Grading was believed to be clear and fair, likely because the rubric was provided to all students. The instructor was credited for motivating interest, perhaps showing that an environment in which students are asked to share their thinking is not necessarily in conflict with the goal of passing students and developing their desire. Lastly, the desire to take more mathematics was significantly higher than the national average, showing that the status quo, the MAA reports we are experiencing in the country, is not, in fact, well justified. There was surprisingly no difference between the NR and the SR groups in whether grading was felt to be clear and fair, likely because the survey results could not determine which group felt agreement to a stronger degree. Similarly, the desire to take more math was similar for both groups, although, again, it did average positively. Most surprising to me was that students' responses to the highlighted feedback. There was an almost uniform distribution of students preferring one over the other. So my conclusion is that students preferred the highlighted feedback, again, in absence of any written feedback, because there was no risk of any comments provoking a negative reaction. However, students did prefer the written feedback because it provided them with clarity about why their mistakes occurred. In both cases, there seems to be an opportunity for improvement in either method. All right, so let's move on to our discussions. In summary, did we accomplish our goal of developing a simple plug-and-play classroom framework that has the potential to work with a variety of students at a variety of levels? Yes, absolutely yes. We showed that this framework has the potential to significantly improve student performance and may result in greater interest in mathematics. It is an attractive option for a majority of students. It correlates with lower drop rates and higher completion rates. On top of that, students credit the framework for their feelings of success. So if we recall Hattie's findings, where did we fall? We fell right on target with an effect size of about 0.73, which is higher than the effect size of prior ability, teacher clarity, homework, performance goals, and learning goals. So to what do I credit this elevated effect size? Well, it's the self-efficacy which comes with the practice of self-grading. So what do these findings mean in context? Well, in context of teaching theory, it means that grades do not serve the role that we think they do. ample grades are not a means of ensuring student success, but a demoralizing distraction that prevents students from relaxing and effectively learning. In terms of teaching practice, this study shows that the MAA's findings need not be the case. Student-teacher disconnect was properly bridged with the use of this framework, and a variety of students were successfully managed. On top of that, students left with higher interest than when they arrived in the course. These results become even more significant when one recalls that this was my very first semester teaching Calc 1, and it was my second semester teaching for anybody at any level. These results are likely trivial in comparison to what a teacher with greater knowledge and greater experience than I had might accomplish with the aid of the self-reflection framework. So this brings us to my recommendations for the fields of future research. There remains much to be explored in terms of how this framework might affect different ages and different subjects. Also, my question is, would the effects be the same if participation was made mandatory instead of optional? As a side note, this is actually going to be something that we explore for the remainder of the semester. As a result of the coronavirus and us teaching everything online, we are going to be moving our entire class to mandatory participation of the self-reflection framework so as to ease any burden in trying to deliver feedback. Now, so I will keep you all posted on that. But lastly, and this one is important, I am curious about the effect of implementing this framework in classes preceding Calc 1. It was a shame that students had to balance calibrating to the new framework in tandem to learning the difficult subject that is calculus. Although the effect was ultimately greater performance, I can't help but to feel that if students had entered the classroom having used this framework to establish their self-efficacy in an earlier math class, perhaps pre-calculus, that their success would have been even greater. Perhaps this is the key to one day optimizing calculus performance, the development of strong student self-efficacy before they arrive on their first day. So in conclusion, 50 years ago, Robert White challenged us to grow as a calculus education. And in those 50 years, the MAA reports that we seem to have made little progress. There is now support for instructors, educators, and administrators to put into place classroom practices that undervalue grades and instead attend to students' learning and conceptual development. This framework, the self-reflection framework, provides a means of bridging traditional administrative requirements which heavily rely on grades, and a means of issuing them that doesn't sacrifice the benefits of self-grading. So it is with great hope that this year at NIU marks a transition. By further exploring the effect of self-reflection framework, we do stand to gain greater student success in Calc 1, and finally make strides towards Robert White's dream of turning calculus from a filter into a pump. So at this time, I would like to thank everybody for attending. I would like to very much thank my thesis advisory committee for supporting me through this process. And then I will open myself up to any questions from anybody who is attending. So Dr. Grebesi, is there any plan to have a follow-up with performance in later courses? I would like to. I don't have one, a plan at this time. I think the infrastructure might be something that we would still need to kind of develop for that. But I do think that that's going to be the number one indicator of student success would be not necessarily passing the course, but passing a later course. But it is nice to know that the same instructors who are grading their final will be potentially grading their next course, and that those grades seem to show that they were doing quite well. All right. All right, I see Eric. So Eric, I've got you unmuted. I saw your hand raised. Did you have a question?
Yeah, so great job, by the way.
Thank you.
Fantastic. So I liked your sort of summary that you gave at the end, and I'm wondering. So one of the things I was thinking is that ultimately, right, like what gets decided as so to Dr. Grubb's point, is there any follow up on how people do later? But ultimately, what gets determined to be success in mathematics is practicing mathematicians. And so one of the things I'm thinking is that because there I could see that the idea that like we don't sort of give what mathematicians might give as might claim as objective feedback, that could be a drawback. But to your point, so to sort of bridge the gap between the idea, well, I mean, if we don't like give more grades and stuff like that, how are we really training people to do what mathematicians call mathematics? But to your point, would you think that maybe what you did lends some evidence to the idea that like specifically at NIU or other schools similar to NIU, we have a lot of students that sort of aren't in a psychological place to take that sort of first feedback that comes with just a score?
Yeah, I don't think it's only something about NIU. I think
No, I know that.
if you
Yeah.
consider like the mathematical trajectory, I think up until calculus, and whether this be AP calculus provided in high
Hmm.
schools or whether it be at universities, I think all of the prior classes are almost structured, maybe with the exception of algebra, as exposing students to a variety of tools that are all available in a box, that then get tucked back away when we move on to the next set of tools. And I think calculus is one of the first times where it starts off with a concept like limits in it, and it builds on that concept for the entirety of Calc 1 and then revisits it in a new context for Calc 2. So if you can't not understand an earlier piece and expect to still succeed in the class overall. So I think it's maybe a good chance to be like, the priority in that subject is to anchor in the notations you have, but also to break your philosophy from one that is simply doing to, like you said, acting as a mathematician, and more allowing yourself the process of discovering and not just taking a grade and putting it behind you.
Thank you.
Yeah. All right, so I see another question, then I'll skip over to the chat box. Suha? Suha, I saw your hand was raised. You're unmuted. Did you have a question?
Yeah, actually, can you hear me?
Yes, I can.
Okay. Well, actually, I wrote my question over there, and it says it's proven that group work is best for students. You know, through researchers, or other research. So how would you implement that? You know, especially we're using an online classes right now, like having the group work in classrooms is different than having a group work online classes. So how would you implement that?
Yeah, so Dr. Grubb and I have been discussing how to kind of work on a digital platform, and how to kind of maybe use some of the tools that we had from the self-reflection option. So I'll give you exposure into how the classroom framework is going to be structured for my students. But what's going to happen is that they are, again, going to be responsible for completing an assignment with effort and giving it good thought, and then submitting a picture of that online. And then I can view to make sure that they completed it with good attempt, and then make a solution key available to them. But what I intend to do online is, because I can't see their work as easily, or I can't share feedback as easily, is just to use the self-reflection option. So I will ask them all to complete a self-reflection worksheet for Tuesday of the following week, and they can use the online classroom collaborate menu, the system, to work with each other to discuss why it is that I attempted something in a specific way, to correct their own work, to ask me questions, and we'll all have the same digital reference, because it'll be them having posted their work, me reviewing their work, and they'll just be trying to complete a reflection.
So you're not planning to use like maybe let's say Zoom or any other visual internet technology with your
No, I
students?
do. I plan on using Blackboard Collaborate, and so that has the option of doing breakout groups. So the overall cadence will be that on Friday of each week, their written homework will be due. I will review it over the weekend, and then I will make a solution key available, and they'll be responsible for checking their work against my solution key for submitting a self-reflection framework or a self-reflection worksheet Tuesday of the following week. So they will essentially own their own learning, and I will just be providing the resources that they will require, as well as help with answering any questions.
Okay, thank you so much.
Yeah, no problem. I'm gonna put you back on
Luck.
mute, and then I'm gonna check the chat box here and see if there are any others that popped in. Let's see. How do I feel I benefited as an instructor professionally and personally? I can honestly say the first semester that I taught Calc 3, bless my students, because I went through so much variation in such a short time frame as I began to discover what my teaching style was. And it really showed me the, 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 the limited value I could give as simply somebody who presented information versus somebody who set forth proper challenges. So I think this is kind of me throwing a lot of my philosophy into a simple system that gets students' attention where they struggle the most often, and teaches me that as an instructor, it's more about trying to give them opportunities to develop their own strengths than trying to download material into their brains. Let's see, another questions. Was there any data collected regarding the gender, racial, and age distributions of the participants? I did not do anything for the race and the age, although, and I am horrible at this, and we will take this not only with a grain, but a lump of salt, the class's appearance seemed not much different from the national averages I had read through the MAA survey. So or at least for NIU as a whole, I should say, not the national average. So the class seemed representative of those who would be attending an NIU class, and the gender distribution seemed similar to the national averages. Although I did not feel comfortable asking for that information, so I didn't. Let's see. Oh, I should mention that all students reported majors, however, did directly match with the national averages. There was no statistical difference in any of the majors being pursued and those that you would expect across the country. Let's see. In what ways was I inspired by my work? I really found that the most interesting aspect of this project was that students, almost regardless of their prior ability, who worked via the self-reflection option, caught up with the students who were the most naturally mathematically adept, who chose not to participate in this option. And instead they participated in the natural framework. So what that tells me is that the number, or a very large factor of calculus success, is not in being good at math, it's not in prior ability, and it's not preordained. It's their willingness to put forth additional work, to put their attention to where it matters most. And I think that was shown because I had plenty of students who were quite good, and by the end of the semester they were struggling, whereas I had seen growth in a majority of students in the other group. All right, I'm gonna check through. I don't see any more. Do I see another hand raised? Let's see. I do not. Oh, I see one more. All right, so Eric, I'm gonna take you off of mute. Can you hear me?
Yeah, one more question
Yeah.
off of what you just said. So do you think maybe that sort of in the details of your statistical analyses and the data you have collected, that there's some evidence maybe to suggest that just the act of self-reflection sort of builds up the ability to persist?
Oh, absolutely.
I mean,
Yeah, that
right. So not just the technical skills, but that the act of self-reflecting would make people more immune to future sort of bad scores that might be taken very negatively otherwise.
Yeah, absolutely.
Yeah.
The self-efficacy that I refer to is a student's belief that they can affect their own success, and that
Okay.
the number one, or the second, self-reported grades is the second highest influence according to Hattie's research. Student self-efficacy is probably, I think, the number sixth. So it's a very high impact, because obviously as a result of belief comes effort and comes attention and comes mechanics, as you will. And as we all know, in Calc 1, you can't just pass the course with an attitude of do a derivative if all else fails. So it kind of like helps to really, yeah, set up their mindset, and then I think they pursue everything else a little bit as a result of it. As a little bit of information, the number one factor, according to Hattie, is teacher efficacy. So whether or not a teacher believes that the work that they are doing is effective. So as a little asterisk to this entire presentation, I think that this could all be absolutely destroyed if it was given to a teacher and mandated that they practice. So instead, I do think that there's a lot of benefit to informing teachers as to the potential benefits of the self-reflection option, and then persuading them to pursue it on their own, as opposed to an administrator mandating it. I'm trying to get Eric back on, but I think you'll have to unmute yourself, Eric.
Yeah, no, I'm really sorry. I was moving around, so I muted myself, and then I realized I didn't have control.
Oh, okay,
So,
I got you.
no, thank you very much for your answer.
Does that work? Good.
Yeah.
All right. Let's see. I think that is all. So we are about out of time. If there's any other questions, you all are welcome to raise your hand, but we are at the point when I will need to move this into the private session. Dr. Grubb, let me unmute you.
I'm just curious if there's any difficulties you foresee in implementing something like this mid-semester as we're in right now.
I think that the number one difficulty would be if the teacher was not well versed in the reasons for the change, because again, it's going to be up to the teacher to be selling this and to believing it, and to be believing it themselves. Otherwise, they can very much affect the culture of their own classroom. Do I think there's anything else? I think change is hard and it can be difficult for students regardless. But beyond that, I think it's going to be quite a. I got nothing but positive attitudes from students. So I think they honestly came at it from a sense of relief and being like, yay, my grades are going to come easy now. And then I think they kind of just naturally started to develop their own skill set and realize that there was a method to all the madness. I did just see another question come in. Did you find any gaps in the rubric? Was each level moving towards mastery described well enough for the students to understand? There were a few changes that I made to the rubric versus the one that Grades Like North used. First, Grades Like North uses a 4-point scale for communicating their grades or their scores or their abilities, and we had to do a traditional 100 percentage point system. We also run on an 85, 75, 60, 50 grading scale, which is different than the 10% blocks that are normally assumed. I did have to make one additional, or I did choose, I should say, to make one additional category underneath the, in one of the lower levels of understanding versus the Grades Like North rubric. That one I think had a lowest score available of 50, and I decided that I wanted to move some of the elements that were about students making an effort, even if the effort was wrong, to a score that was more around a 20% mark. But I think that was just because it aligned with my personal teaching philosophy as well as the college atmosphere versus the high school atmosphere. But as I kind of showed through the data for question 7, I really don't think that the rubric, where the point values were in the rubric made too much of a difference to the success. I think it was just, did the rubric itself promote mastery moving up, and where the points in line with the teacher's philosophy. So I think there's potential for students or teachers to adjust the rubric to whatever they might care to have. Okay. Thank you, everybody, for your attending. If those of the committee would mind just staying on, and then I am going to ask everybody to please remove yourselves from the meeting. And thank you again so much for attending. Stay safe out there and keep teaching.